What if the Earth's heart, hidden far below the surface, carries within it a quiet source of heat that has never truly gone out, a warmth older than mountains and oceans, older even than the air we breathe? To imagine this, we must place ourselves in a scale that is both vast and intimate at once, a time before memory, when the planet was still young, gathering its shape from dust and fire. In those first moments, collisions of stones, fragments, and wandering bodies released unimaginable energy. The Earth grew hot, so hot that much of it melted into a glowing sphere. Some of that ancient heat has slowly faded, escaping into space, but part of it has remained, trapped deep inside, like embers beneath thick layers of ash. Now, billions of years later, it is still there, silent, invisible, yet quietly present. This heat does not sleep. It moves, it rises, it reshapes the crust above. We see it in volcanoes, where molten rock escapes upward. We feel it in earthquakes, when slow shifts in the mantle release tension. But most of the time, it works in ways we cannot sense, hidden, steady, shaping the planet patiently. To understand why the core is still warm, we can imagine a kettle left on a stove. Even when the flame is turned off, the water stays hot for a long time, cooling only slowly. The Earth's kettle, however, is much larger and its lid is much thicker, so the cooling stretches across spans of time that overwhelm human scales. What to us is eternity is, to the planet, just a passing moment. And yet, as simple as this sounds, the story is not fully told. Because heat does not come only from the beginning. There is also another, quieter source, hidden in the elements themselves. Some atoms deep in the Earth are unstable, and over time they change, releasing small bursts of energy. This is radioactive decay. It is not explosive here, not dangerous in the way we sometimes imagine radiation, but rather a steady drip, like drops of water filling a jar over millions of years. These drops keep adding warmth to the core, ensuring that the ember does not fade completely. We cannot directly measure this warmth. We do not have instruments that reach so far, nor drills that can descend even a fraction of the distance. Instead, we read traces. We look at rocks from ancient eruptions, at minerals that trapped isotopes long ago, at patterns in volcanic chains. These are the quiet archives left on the surface, whispering of a deep engine below. Sometimes we look to other worlds for comparison. The moon, smaller and less protected, has cooled much more quickly. Its volcanoes are silent now. Mars too seems to have lost much of its heat, its field of magnetism gone, its interior quieter than before. By contrast, Earth still stirs, still breathes from within. The difference may lie in size, in composition, or in the balance of radioactive elements. We do not fully know, and here our knowledge bends into uncertainty. Yet absence of proof does not mean absence of process. The signs that remain suggest that heat continues to flow upward, slowly but steadily. Let us pause and imagine a small experiment. Suppose, just in thought, that all this inner heat suddenly vanished, cooling the core completely. Over centuries, the mantle would stiffen, volcanoes would quiet, the magnetic field would weaken. Without that shield, solar winds might strip our atmosphere, and the sky we know could thin into something unfamiliar. Now let us imagine the opposite, that the heat increased rather than faded. More eruptions, more shifting plates, perhaps a planet far less stable, less forgiving. Neither of these extremes is our world, but by picturing them, we begin to understand how delicate the balance is, how the core's warmth has shaped the long comfort of our surface. The true story, as always, is gentler. The core continues to cool, but so slowly that the span of all human history is hardly a blink in its rhythm. Our cities rise and fall while its ember burns on, untroubled. The traces we study, the minerals, the magnetic lines, the volcanic stones, are the closest we can come to listening to that rhythm. They are not perfect, they leave gaps, but together they offer a soft murmur of the hidden fire. In the end, we cannot claim certainty. We can only trace outlines, gather hints, and imagine patiently. The heat of the Earth's core may be ancient, it may be replenished, it may change in ways we do not yet suspect. What matters is that it continues, quietly, steadily, shaping the ground we walk upon. This thought is less a conclusion than a pause, a reminder that the mysteries below are still unfolding, in silence, in time, beyond our sight yet always beneath our steps. What if the silence of the Earth's core is not a sign of simplicity but a reminder of how much remains hidden from us, a quiet resistance to certainty? We have learned to picture the inner layers through echoes, through shifting fields, through faint traces locked into stone. Yet even with all this, the details remain blurred. The deeper we go in thought, the less solid our knowledge becomes, like walking into fog where shapes are suggested but never fully clear. This is not failure, but the nature of studying something so far beyond reach. Now we linger for a moment on the limits themselves. We cannot drill to the core. Our deepest boreholes reach barely a fraction of the crust. We cannot place instruments where the pressure would crush any device. Instead, we listen from afar. Seismic waves provide clues, but their interpretations vary. Magnetic records tell of change, but not always of cause. Even computer models, powerful as they are, depend on assumptions. The result is a field of knowledge full of possibilities, where each new discovery often raises as many questions as it resolves. Let us pause and remember that uncertainty is not emptiness. It is a form of knowledge in itself. To admit what we do not know keeps us open to new signs. It prevents us from mistaking the present models for final truth. In science, humility is as important as discovery. Now we turn gently toward the traces again, the language of indirect signs. Rocks carry memories of magnetic reversals. Lava flows preserve alignments of ancient fields. The seafloor records patterns of spreading and shifting. Even the slow drift of continents is a surface echo of deeper movements. Each piece is incomplete, but together they form a mosaic. We do not see the core itself, but we see its influence everywhere, written across the skin of the planet. And yet, interpretation remains cautious. Two different models may explain the same trace in different ways. A variation in seismic travel time could mean changes in temperature, or changes in composition, or even layered structures we have not considered. In this way, the Earth offers us riddles rather than statements. Now let us imagine for a moment a world where certainty were possible. Suppose we could look directly into the core, see every movement, measure every temperature. The mystery would vanish. Our knowledge would be exact, but the sense of wonder might lessen. The unknown itself is part of what gives depth to our study, part of what draws us back to listen again. On the other side of the thought, let us imagine a world where no traces reached us at all. No waves to measure, no magnetic memory in rocks, no signs on the surface. Then the core would be nothing but speculation, a hollow idea without grounding. In such a case, we would know far less, and our connection to the deep earth would be weaker. Our reality is between these two extremes. We do not know everything, but we are not blind. We walk a path of fragments, gathering signs where we can, building models that are useful but always temporary. This is how science often moves, not in sudden revelations, but in gradual refinement, with humility as companion. Now we may gently step back and see the broader rhythm. The uncertainty of the core is not an obstacle but part of its nature. Its silence forces us to be patient. Its distance reminds us of scale. It teaches us that knowledge is never complete, and that even absence of direct proof leaves room for imagination. And so we end here with a pause, holding both the traces we have and the shadows we cannot yet fill. The Earth's core remains a place of quiet uncertainty, a hidden heart that resists full clarity, leaving us with the reminder that not knowing is also part of knowing, and that in the soft balance between evidence and mystery lies the rhythm of discovery itself. What if the deepest part of our planet is made mostly of materials that feel familiar in our daily lives, and yet, under such immense pressure and heat, behave in ways we can scarcely imagine? The inner Earth is thought to be largely iron, with nickel as a companion. These are metals we know well. We see them in keys, in tools, in coins that pass through our hand. They are solid, heavy, and strong. But deep in the core, these same elements are subjected to conditions so extreme that their character changes. At pressures millions of times greater than the air we breathe, atoms are pushed into arrangements that do not exist at the surface. Iron may crystallize into unfamiliar forms, its structure bending to the weight of the world above it. Nickel, too, may shift, blending with iron to form alloys that behave differently than anything we have seen in a laboratory. This picture is not one of direct evidence but of inference. We cannot travel there to sample these metals. Instead, we learn through experiments that recreate fragments of the pressure, through calculations that model how atoms might behave, and through the patterns of seismic waves that reveal densities and speeds. These are indirect signals, each offering a piece of the puzzle. Together, they suggest that iron and nickel dominate, but likely not alone. Now we pause to admit that uncertainty remains. Some researchers propose that lighter elements may be mixed into the core: oxygen, sulfur, silicon, perhaps even hydrogen. These elements, though less dense, could dissolve into the metallic ocean of the outer core, changing its flow, shaping the way the magnetic field is generated. We do not yet know how much of these lighter companions exist, or how evenly they are distributed. What is clear is that the inner Earth is not pure, not simple, but a blend whose recipe is still unfolding. Let us gently linger on the traces again. Meteorites, the remnants of early solar system building blocks, provide one kind of clue. Some are made of iron and nickel, similar to what we believe lies at the center of our planet. By studying their chemistry, we gain insights into what materials may have sunk inward during Earth's formation. Yet meteorites are not Earth itself, and their histories differ. Another clue comes from the density of the planet as a whole. We know how heavy the Earth is, and we know the densities of surface rocks. By subtracting one from the other, we infer that the hidden heart must be far denser than what lies above. Still, these are estimates, not direct measurements. Now we allow ourselves a thought experiment. Imagine that the core were made of something very different, not iron, but perhaps silicates, the minerals common in the crust. In such a case, the Earth's density would be too low, the magnetic field might never have formed, and the planet could be less protected from solar winds. Life as we know it might have struggled to take root. Now imagine the opposite extreme, that the core contained far more light elements than we suspect. The density would shift, the balance of pressures would change, and the magnetic shield could behave differently, perhaps weaker, perhaps more unstable. In reality, our Earth seems to sit between these possibilities, with iron and nickel forming the base, and lighter elements mixed in subtle proportions. And here we pause once more. The chemistry of the core is a story told through fragments, through meteorites, through lab experiments that reach only part of the needed pressures, through waves traveling thousands of kilometers beneath us. It is a story without finality. Each new measurement refines the picture, sometimes confirming, sometimes challenging what we thought we knew. The language of metals in the deep earth is not fully written, but enough of it has been revealed to remind us of scale and mystery. So we leave this reflection with a gentle awareness. The metals we hold in our hands, cold and solid, have cousins deep below that are reshaped by unimaginable forces. The core is not alien, but neither is it familiar. It is a place where the ordinary becomes extraordinary, where iron and nickel write the story of a planet from within, in silence, in pressure, and in time. What if the weight pressing down on the Earth's core is so immense that it changes the very behavior of matter, forcing it into states we can hardly recreate or imagine? At the surface, we think of heat as something that melts, softens, and loosens. But deep below, the rules bend. There, temperature and pressure are locked in a constant contest. The heat of the core is enough to keep metals in a molten state, yet the crushing load of the planet above is so powerful that even in extreme heat, parts of the core are solid. pressure here means the force exerted by all the layers of rock and mantle resting above. To picture it simply, we might imagine stacking countless blankets on top of one another, until their collective weight prevents even a warm object beneath them from expanding. In the Earth's center, those blankets are replaced by thousands of kilometers of rock, all pressing downward. The result is a world where iron can be as hot as the surface of the sun and still remain in a solid form, its atoms locked tightly together by the sheer force around them. Now we pause and note how we come to such knowledge. No instrument has touched the inner core. We rely on experiments in laboratories that use diamond anvils and lasers to recreate a fraction of those conditions. Even then, the results are partial. Seismic waves, traveling from earthquakes, provide another clue. Their speed tells us something about density and rigidity. From these traces, we infer the balance of heat and pressure inside. Yet each method has limits, and interpretations vary. The truth of how matter behaves at such extremes is still uncertain, and we hold our conclusions with care. The language of traces is subtle but steady. When shear waves travel through the earth, they reveal the presence of solids. When compressional waves bend and slow, they mark transitions between liquid and solid layers. Combined, these echoes suggest a solid inner core surrounded by a liquid outer shell, a structure that exists only because pressure and heat are so finely balanced. Without the immense weight above, the inner part would be liquid. Without the intense heat, the outer part would be solid. It is the balance itself that shapes the planet's hidden heart. Now let us allow ourselves a thought experiment. Imagine, in one step, that the Earth were smaller, with less weight pressing down. The heat at the center would then be enough to keep everything liquid. In such a case, the inner core might never form. Without that solid heart, the outer core's flows might behave differently, perhaps less stable, perhaps less able to sustain the magnetic field. Over long ages, the shield protecting our planet from solar winds could weaken or disappear. Now take the opposite step. Imagine an Earth with greater mass, its pressure so strong that even the outer core could freeze despite the heat. A fully solid heart might mean the end of the geodynamo, the magnetic generator we rely on. The planet would grow still inside, and the surface might eventually lose its protection. In both imagined worlds, balance is lost. Our real Earth rests in between, its layers shaped by a delicate equilibrium of heat rising and pressure containing. The core we know today is the product of this balance, though we must admit how incomplete our understanding is. Now we gently return to the present. We see the evidence not directly but in archives written in stone, in patterns of magnetic minerals, in the spreading of ocean floors. These signs confirm that the balance of heat and pressure has endured across billions of years, keeping the core active, keeping the field alive. Yet we also know the system is not fixed. The inner core is slowly growing as more of the liquid solidifies under pressure. The outer shell is gradually thinning. These processes unfold so slowly that they remain invisible in a human lifetime, but in the scale of geologic time they matter deeply. And so we pause with a quiet awareness. The Earth's core is a place where heat and weight coexist, where iron bends to laws that seem almost contradictory, molten and solid, hot and frozen, depending on where one looks. It is a reminder that the rules of matter are not absolute but shaped by context. Pressure, invisible to us on the surface, defines what is possible in the depth. We hold this thought not as a final certainty but as an open image, a recognition of how much lies hidden in silence beneath our steps. What if some of the warmth we still feel rising from inside the Earth is not new at all, but a memory from its very beginning, a lingering trace of birth? More than 4 billion years ago, the young planet grew from countless collisions. Dust and rocks, fragments of larger bodies, came together under gravity. Each impact released enormous energy, heating the surface until much of it became molten. For a time, Earth was less like the stable world we know and more like a glowing sphere, restless and unshaped. As the outer layers cooled and hardened, Much of that original heat escaped into space. But not all of it. A portion was trapped deep inside, unable to find its way out quickly. That remnant, sealed under thick layers, still glows faintly today. Now we pause for a moment to picture this. We can think of it like a cast iron pan fresh from the fire. Long after the flame is gone, the pan stays hot, radiating warmth. The Earth is far larger and far better insulated, so its cooling stretches across billions of years rather than minutes. The warmth we sense in volcanoes, in hot springs, in the slow rise of continents is, in part, a memory of those early collisions. But the details of how much heat remains and where are uncertain. We cannot see directly into the past. We build models from fragments, meteorites that carry chemical signatures of the early solar system, rocks that bear traces of ancient processes, calculations of how quickly a body of Earth's size should cool. These are guides, not certainties. Some studies suggest much of the primordial heat has already escaped. Others suggest that deep regions still hold reservoirs of energy, insulated by thickness and pressure. Both views may hold some truth. Now we linger on the traces that confirm this hidden ember. The very movement of tectonic plates requires heat from below. Without it, the mantle would be rigid, continents would rest in silence. The activity of volcanoes is another marker, magma rising where mantle plumes bring ancient warmth upward. Even the slow drift of magnetic field patterns hints that deep motions, powered partly by residual heat, continue still. These signs remind us that the Earth's early fire has not gone out. Let us wander into a gentle thought experiment. Suppose, in one step, that the Earth had cooled much faster, losing its primordial heat within the first billion years. The mantle might have hardened early, plate tectonics might never have formed. In such a case, the recycling of surface materials, the process that renews crust, regulates atmosphere, and supports long-term stability, could have been absent. The Earth's surface might resemble that of the Moon, frozen and unchanging. Now take the opposite step. Imagine that the Earth had trapped much more of its initial heat, enough that the surface today was still restless with vast oceans of magma. Life as we know it might never have found calm ground to emerge. Oceans would boil, continents would fail to form. The balance we live within is neither of these extremes but something in between. Enough heat has lingered to keep the planet alive with motion, but not so much that the surface is uninhabitable. We must return here to humility. The exact share of Earth's warmth that comes from its birth, as opposed to radioactive decay or other sources, is not fully known. Estimates vary, and methods of calculation leave gaps. The absence of certainty does not mean the absence of process. It only means we still walk among shadows, gathering signs where we can. And so we pause with this thought. Beneath every mountain, beneath every ocean, there is warmth that began with the planet itself, a whisper of the fiery collisions that shaped it. This warmth is a memory not of our time, but of Earth's earliest days, still lingering, still shaping the rhythms of the world. It is a reminder that the deep past is not gone, but continues, quietly, beneath our steps. What if some of the warmth that still rises from the Earth's depths is not just a leftover ember from its beginning, but the result of countless invisible sparks continuing even now? These sparks come from radioactive decay, a process where certain atoms, unstable in their structure, slowly transform into other forms. As they do so, they release small packets of energy. It is not a sudden fire, not an explosion, but a gentle and steady release, like drops of water filling a jar over long spans of time. Deep in the mantle and core, elements such as uranium, thorium, and potassium continue this slow process, adding to the heat that drives motions inside the planet. To grasp this more clearly, we can compare it to a quiet candle in a large room. The flame is small, yet it burns without pause, and over time its heat accumulates. Now we imagine billions of such candles hidden within the Earth, each burning not for minutes or hours but for millions and billions of years. Together, their collective warmth becomes significant, enough to keep parts of the planet active. This radioactive heat is one of the main reasons Earth has not yet cooled into silence. Yet we must pause and recognize what we do not fully know. We cannot directly measure how much of each radioactive element exists in the deep interior. We sample surface rocks, volcanic lavas, and meteorites, and we perform laboratory analyses. From these, we build estimate. Some models suggest radioactive decay provides almost half of Earth's current internal heat. Others suggest less, others more. The uncertainty remains, and we approach it with caution. Now we linger on the traces. Rocks brought up from the mantle sometimes contain isotopes, versions of elements that decay at known rate. By measuring the amounts present, scientists can calculate how much heat must have been released in the past and how much might remain. Even sediments, though far removed from the core, can carry hints of radioactive decay through particles washed down from ancient mountains. These fragments together form archives, not perfect but steady enough to guide our understanding. Now let us wander into a thought experiment. Imagine, first, a world where the Earth contained almost no radioactive element. Without their slow warmth, the planet would have cooled far more quickly after its birth. Plate tectonics might have ceased long ago. Volcanoes would be silent, the mantle rigid, and the magnetic field perhaps faded. The Earth's surface might then resemble Mars with its quiet, frozen crust. Now let us take the opposite step. Suppose the Earth held far more uranium and thorium than it does. The steady heat would be stronger, keeping the mantle more fluid, making eruptions more frequent, continents less stable. Civilizations might struggle to find long stretches of calm ground. The balance we know would be different, perhaps harsher. In reality, our Earth rests somewhere between these extremes. Its radioactive content is not overwhelming, but not absent either. It has been just enough to keep the deep processes alive while leaving the surface stable enough for life to grow. Yet even here we must be careful. The distribution of these elements is not uniform. Some regions of the mantle may be richer, others poorer. Some may concentrate over time while others disperse. Our instruments cannot see these patterns directly, so we build models, compare them with data, and refine them slowly. The picture remains unfinished, and that is part of its nature. And so we pause with this thought. Beneath us, the Earth's warmth is not only a memory of its violent birth, but also the quiet work of atoms changing, steadily, invisibly, across unimaginable spans of time. The heat of radioactive decay is patient, not dramatic, but it sustains the slow breathing of the planet. It leaves traces in rocks, in isotopes, in the restless motions of the mantle. It is not something we can touch or see directly, yet its presence shapes the world we live upon. This reminder, quiet and enduring, leaves us with a gentle awareness of balance, between what fades and what continues, between embers of the past and sparks of the present. What if the slow stirring of liquid iron deep in the earth behaves like a hidden dance, steady and powerful, shaping a shield around our planet? In the outer core, where metals remain molten under immense heat, movement is constant. These flows are not fast like rivers or storms. They are slow, heavy currents, shifting as the earth rotates, rising and falling as heat escapes from deeper layers. This quiet circulation is what we call convection. To picture it simply, we can imagine a pot of water warming on a stove. At first the water seems still, but soon faint movements appear, as hot water rises and cooler water sinks. Over time, these currents form patterns that continue as long as heat flows. In the outer core, the liquid is not water but iron mixed with other elements, and the scales are far larger, stretching across thousands of kilometers. Yet the principle remains the same. Heat drives motion, and motion carries energy. Now we pause and notice what this motion creates. As molten iron moves, it carries electric charges. Moving charges generate magnetism, and this is how the Earth's magnetic field is sustained. The process is often called the geodynamo. It is not a machine built by hands, but a natural engine, one that has operated for billions of years without rest. Its output is invisible, yet its presence is felt in every compass needle and every aurora in the sky. And yet, we must be humble. We do not know the exact patterns of flow inside the outer core. We cannot watch these currents directly. Our knowledge comes from computer simulations, from seismic echoes, from the drifting paths of the magnetic poles. These are indirect hints, signs that suggest rather than prove. Models show swirls and spirals, vortices of metal flowing around the inner core, but whether the Earth truly moves this way is something we cannot yet confirm. What we can say is that convection must exist, because without it the magnetic field could not persist. Now we linger on the traces. Ancient rocks show alignments of magnetic minerals, frozen in place when they cooled. They tell us the field has flipped many times, suggesting the flows inside have changed direction or strength. Sediments on the ocean floor carry similar records, layers upon layers that form a quiet archive of magnetic history. Even measurements taken by satellites reveal patterns. Regions where the field is stronger, regions where it weakens, zones that drift slowly across the globe. All of these signs are footprints of convection far below. Let us allow ourselves a thought experiment. Suppose, in one step, that convection in the outer core ceased. Without these slow currents, the dynamo would fade, the magnetic shield would weaken, and in time it might disappear. Solar winds, unhindered, could erode the atmosphere, thinning the air, changing the balance of surface life. Now take the opposite step. Imagine convection growing more chaotic, with flows faster and more unstable. The magnetic field could fluctuate wildly, poles wandering rapidly, reversals occurring more often. For those on the surface, navigation would be less certain, technologies more vulnerable to geomagnetic storms. Neither of these extremes is what we see today. Our Earth lives in between, with convection steady enough to maintain a long-lasting field, but variable enough to leave marks of change across time. Still, the system is not fixed. The inner core grows slowly, releasing heat that fuels these currents. Radioactive decay contributes as well. Over billions of years, the balance may shift. Convection could weaken, the dynamo could fade. Or it may persist far longer than we imagine, its rhythm continuing quietly beneath our feet. We cannot know with certainty, only trace its history through the language of rocks, sediments, and skies. And so we pause here, with the image of a vast metallic ocean, turning in silence around a solid seed, its slow dance shaping the invisible shield we rely on. It is a reminder that even the gentlest currents, moving with patience across unimaginable spans, can create something enduring, something that reaches far beyond the place where it began. What if the magnetic field that shields our planet has not always been as steady as it seems, but has wandered, weakened, and even flipped its direction many times? To us, the field feels constant. Compasses point north, auroras gather near the poles, satellites orbit within its protection. But the record held in rocks and sediments shows a more restless history. Over millions of years, the poles have exchanged places repeatedly. The process is slow, unfolding across thousands of years, yet its imprint is unmistakable. When lava cools, magnetic minerals inside it align with the direction of the field at that time. Layer upon layer of hardened lava flows have captured these alignments, revealing that what was once north later became south, and then back again. The seafloor itself carries these memories. As new crust forms at ocean ridges, it locks in the magnetic orientation of the field. Over ages, this has created long stripes of reversed and normal magnetization, stretching across entire oceans. They are like a barcode written across the planet, recording each shift of the Earth's inner engine. Now we pause and admit that while we see the pattern, the causes remain uncertain. Some suggest that changes in the flow of molten iron in the outer core disturb the dynamo. Others think the growth of the solid inner core may play a role. It may even be that these reversals are simply part of the natural instability of such a complex system. The absence of certainty reminds us that the field is a dynamic phenomenon, not a fixed structure. The traces tell us what has happened, but not always why. Now we linger on the language of these traces. Rocks from every continent, sediments from ancient lake beds, layers of volcanic flows, all preserve faint but reliable signals of past magnetism. By gathering them, comparing them, and arranging them in time, scientists have built a timeline stretching back hundreds of millions of years. This archive shows long periods of stability, punctuated by sudden reversals. It also shows intervals where the field weakened dramatically, only to recover again. These variations are part of the planet's rhythm, though not one we feel in daily life. Let us wander into a thought experiment. Imagine, in one step, that the field were to weaken completely for a time. The shield against solar wind would thin. More charged particles would reach the atmosphere, increasing radiation at the surface. Satellites and electrical systems might suffer. Life, however, might adapt, as it has through past reversals. After centuries, the field could recover, perhaps with poles swapped. Now take another step. Imagine that reversals became frequent, occurring every few thousand years instead of hundreds of thousands. Compasses would be unreliable, migratory animals could face confusion, and societies dependent on magnetic navigation would need constant adjustment. The field would still exist, but its behavior would feel far less predictable. In reality, what we see is somewhere in between. The field drifts, reverses, weakens, and strengthens, but always returns. Its rhythm is irregular, without clear cycles, but its presence has endured for billions of years. It may flicker, but it has never failed entirely. This endurance is what makes the Earth different from Mars, whose field faded long ago, leaving its surface bare to the wind of the sun. And so we pause here, with the thought that the magnetic field is not a fixed shield but a living one, shaped by the slow currents of molten metal deep inside. Its wandering poles and sudden reversals are not signs of failure but of vitality, reminders that even protective veils have their own rhythms. What we hold is not certainty but a recognition of patterns, written quietly into stone, layered patiently by time, whispering of a restless shield that has always been part of Earth's story. What if the auroras we see shimmering in the sky are not only spectacles of light but also faint messages from the Earth's hidden core, carried upward through layers of atmosphere and space? The green and red curtains that dance above polar regions are the visible part of a chain that begins deep within. The molten iron of the outer core generates the magnetic field. That field reaches far beyond the surface, forming a protective bubble. When solar particles arrive, guided by this field, they funnel toward the poles and meet the thin air of the upper atmosphere. There, collisions with oxygen and nitrogen release light, painting the sky in slow wave. In this way, the invisible motion of metals far below creates beauty far above. Now we pause to notice the scale. The core is thousands of kilometers beneath us, the auroras hundreds above. Yet they are connected by the magnetic lines that run silently between them. The lights in the sky are indirect traces of currents we cannot see. They are like glowing signatures of the deep earth, written in the canvas of the night. And yet, as with so much else, our knowledge is incomplete. We know that auroras reflect the strength and shape of the magnetic field. But we cannot map every detail of that connection. Sometimes the lights appear in arcs, sometimes in rippling sheets, sometimes as sudden bursts. These patterns depend on the flow of particles from the sun, but also on variations in the field below. The exact relationship is not fully understood. The language of auroras is clear in beauty, less so in meaning. Still, they are archives of sorts. Ancient peoples carved them into myths and stories, preserving memory of unusual skies. Modern instruments record their colors and intensities, linking them with geomagnetic activity. Even ice cores keep subtle traces, as solar storms leave chemical imprints in polar snow. Together, these records remind us that the Earth's shield has long been in dialogue with the sun, and auroras are the visible outcome. Now let us imagine a thought experiment. Suppose, in one step, that the magnetic field were to weaken significantly. The auroras would grow stronger and appear farther from the poles, lighting skies in regions unaccustomed to them. The beauty would expand, but so would exposure to solar radiation. Satellites could fail, power systems could falter, and the shield would be less protective. Now take another step. Imagine instead that the field grew stronger than ever before. The auroras would shrink toward the poles, perhaps dimming, perhaps becoming rarer. The shield would be robust, but the sky would lose one of its quietest wonders. In both imagined cases, auroras reflect the balance of deep forces, translating hidden flows into visible forms. And here we return to humility. The lights we admire are only the surface of a vast system. They tell us that the Earth's core still moves, still generates a field, still protects. But they do not reveal the full detail of how or why. They are hints, traces, whispers in color. To hold this thought is to see auroras not just as beauty, but as the language of the planet itself, messages from the heart of the Earth, carried upward and painted softly in the night sky. They remind us of connection across scales, from molten iron to magnetism, from particles of the sun to glowing air, from deep silence to fleeting light. And so we pause here, with the gentle awareness that every aurora is more than spectacle. It is a sign that the hidden core still breathes, its unseen motions reaching outward, leaving traces where the Earth meets the sky. What if the Earth's inner workings could be compared to a gentle tide, rising and falling not in hours but in cycles that span millions of years? These deep rhythms are not felt in the way we feel waves at the shore, yet they guide the planet's long-term behavior. Inside the outer core, currents of molten iron flow, sometimes faster, sometimes slower, sometimes in patterns that shift over time. These changes, though invisible, leave traces in the magnetic field. They appear as slow drifts of the poles, as variations in field strength, as periods of calm interrupted by reversals. In this way, the core carries its own rhythm, one that does not align with human time but belongs to the scale of the Earth itself. Now we pause and reflect on the idea of cycles. We often think of cycles as regular, like the seasons or the phases of the moon. But the rhythms of the core are less predictable. They are irregular, their patterns only partly understood. Some intervals between magnetic reversals are short, others very long. The field weakens and recovers, but not in exact repetition. Still, when we look across vast spans of history, a kind of rhythm appears, not steady but persistent, like a melody played with pauses and variations. To study these rhythms, we rely on archives. Rocks and sediments preserve the alignment of magnetic minerals. Ice cores capture traces of solar particles, themselves guided by the state of the field. Even archaeological artifacts, baked in ancient fires, sometimes hold tiny magnetic imprints that tell us about the field at the time of their creation. Each of these is a note in the larger composition. Together they reveal that the Earth's field has never been truly still, but has always been in motion, breathing slowly with the planet. Now we pause to admit how much remains uncertain. We do not know exactly what drives these deep rhythms. They may be linked to convection in the outer core, to the growth of the inner core, or to interactions between layers we cannot see. It may even be that chance and complexity together produce patterns that only appear cyclical when viewed from afar. The absence of clear cause reminds us that the Earth's deep time does not always match human desire for order. Now let us wander into a thought experiment. Imagine, in one step, that the rhythms of the core suddenly quickened. Reversals would come often, perhaps every few thousand years. The field would weaken and strengthen rapidly, creating more frequent auroras, more disruptions to satellites, more challenges for animals that navigate by magnetism. The planet would still be shielded, but less steadily. Now take another step. Imagine the opposite, that the rhythms slowed to stillness, the outer core ceasing to stir. The magnetic field might fade gradually, leaving the Earth exposed to solar winds. Over time, the atmosphere could thin, much as it did on Mars. Life would face a quieter but harsher world. Neither of these extremes is our reality. Instead, we live within a balance, where the core's rhythms are slow enough to provide continuity, yet dynamic enough to remind us of change. The surface may feel stable in our brief lifetimes, but the archives show otherwise. Beneath the calm, the planet is always breathing. And so we close this reflection with a gentle awareness. The Earth's core carries its own music, one too slow for us to hear directly, but one that leaves echoes in rocks, in skies, in the drifting of poles. It is a rhythm of deep time, neither steady nor silent, shaping the world with patience. To notice it is not to solve it, but simply to recognize that even the deepest silence of the Earth is full of hidden movement. What if the Earth's hidden heart is not uniform at all, but holds variations, patches of difference that stretch across thousands of kilometers? We often picture the core as neat and spherical, solid within, liquid without. Yet traces suggest it may be more complex. Seismic waves do not travel through it evenly. In some directions they move faster, in others slower. This hints at anisotropy, a word meaning that properties change depending on orientation. It is as if the iron crystals in the inner core are aligned like fibers in wood, making waves pass differently along the grain than across it. This quiet irregularity is a clue to processes we cannot see directly. Now let us pause and think of why this matters. If the inner core is anisotropic, it may be growing unevenly. Some regions could be crystallizing faster than others, perhaps because heat escapes more easily in certain directions. Over millions of years, this uneven growth may have left the inner sphere slightly lopsided, shifting the balance of flows in the outer core. Such details, though hidden, could shape the behavior of the magnetic field at the surface. But here we must admit uncertainty. We cannot drill to confirm these patterns. Our models depend on how seismic waves bend and scatter, and interpretations differ. Some studies suggest strong anisotropy, others weaker. Some even propose that the alignment changes over time, like a compass needle slowly turning. Absence of direct observation leaves us cautious. The language of traces is subtle. Earthquakes, recorded across decades, provide wave paths through different parts of the core. By comparing them, scientists notice small differences in travel time, sometimes only a fraction of a second. These minute signals, repeated across many events, hint at structure. They are not loud declarations, but whispers requiring careful listening. Now let us linger on a thought experiment. Imagine, in one step, that the inner core were perfectly uniform. Waves would travel the same in every direction. The field generated by the outer core might also behave more steadily, with fewer irregularities. Our compasses would still point north, but the magnetic poles might wander less. Now imagine the opposite. Suppose the inner core had extreme anisotropy, with strong differences across regions. The flows in the outer core could be influenced unevenly, the magnetic field shifting more often, reversals perhaps occurring at different intervals. The shield above us would still exist, but its behavior could be more restless. Our reality lies somewhere between. The inner core is not perfectly uniform, nor wildly irregular. It seems to hold patterns of subtle difference, enough to influence but not overwhelm. These patterns remind us that even the deepest sphere is not static. It grows, shifts, perhaps even rotates at a pace slightly different from the surface. We cannot see these processes directly, but the traces accumulate in archives. Rock magnetism, wave paths, drifting poles. They suggest a core both ordered and uneven, both stable and dynamic. And so we pause with this awareness. Beneath us lies not a perfect sphere but a place textured by deep forces, its irregularities shaping the rhythms we feel only indirectly. To reflect on this is to accept that even at the planet's heart, complexity endures, reminding us that nature rarely chooses simplicity, and that mystery is often hidden not in the absence of order but in the quiet presence of variation. What if the ground beneath us is not a single, solid piece, but a set of hidden layers, each one different, each one carrying its own quiet story? When we stand on soil, it feels firm, almost final, but beneath that surface lies a gradual deepening of scales. The outer crust, thin and fragile, stretches like a delicate skin. It is only a few dozen kilometers thick in most places, which compared to the size of the Earth is almost nothing, like the peel of an apple compared to its whole. Beneath this skin lies the mantle, vast and heavy, made of rock that moves slowly over time, not like water but not fully rigid either, more like warm wax that bends and shifts across ages. And then, deeper still, there is the core, the densest part, rich in metals, far beyond reach. We picture it as two regions, a liquid outer sphere and a solid inner heart. We do not see these layers directly. Our understanding comes from listening, from measuring, from piecing together fragments. Seismic waves from earthquakes travel differently through rock, through liquid, through solid. By tracing their paths, we begin to sketch outlines of what lies far below. It is like hearing echoes in a dark cavern, trying to imagine the size and shape of the chamber only from the way sound returns. The details remain uncertain, yet the broad pattern is consistent, suggesting that Earth's interior is indeed divided into shells, each with its own character. Now we pause and imagine what these layers mean in time. The crust is where rivers cut valleys, where mountains rise and crumble, where life has left its marks. It changes quickly, at least by geological standards. The mantle moves more slowly, but its slow currents push the crust, giving us drifting continents, opening oceans, raising ranges. The core is slower still, yet its motions generate the planet's magnetic shield, a process we sense only indirectly. Each layer operates on its own rhythm, yet all are connected, forming a chain of cause and effect that stretches across the whole Earth. Still, there are limits to what we know. Our drills barely scratch the crust. We have never touched the mantle, never sampled the core. The deepest boreholes reach only a fraction of the distance, like pricking the surface of a vast fruit and trying to imagine its center. So we rely on signs instead. The chemistry of volcanic rocks that rise from below, the way seismic echoes bend and scatter, the slow drift of continents mapped across centuries. Each of these is a trace, a marker, an archive left for us to interpret. They are not complete, but together they form a kind of language. Reading this language takes patience. For example, certain volcanic rocks carry minerals that could only have formed under pressures far greater than the surface ever experiences. From them, we learn something about the deep mantle. The alignment of crystals in ancient lava flows shows us how Earth's magnetic field has shifted, hinting at the movements of molten metal deep inside. Even the spreading patterns of the ocean floor record the restless breathing of the crust. These are all indirect, but they guide us. Now let us drift into a thought experiment. Imagine the Earth without its layered structure, a single block of stone, uniform and unchanging. Without a mantle moving beneath the crust, continents would never drift. Oceans might never have formed in their current shape. Mountains could rise only once, then crumble without renewal. Without the liquid outer core, the magnetic field would not exist, leaving the surface more vulnerable to the sun's winds. Life itself might have been shaped differently, perhaps never reaching the forms we know. In another step, let us imagine the layers shifting too quickly, the mantle flowing like water instead of wax. The crust above would fracture constantly, continents splitting apart in centuries instead of millions of years. The surface would be unstable, harsh, perhaps too unstable for long civilizations to settle. Neither of these extremes matches the Earth we inhabit. What we have instead is balance. Layers that differ but cooperate across immense spans of time, each one giving shape to the others. We should be cautious here. Much of what we picture is still uncertain. We cannot say with absolute clarity what the boundary between mantle and core truly looks like. Some think it is sharp, some think it may blur across a zone of mixed material. Our models depend on limited data, and every improvement in measurement changes the picture slightly. But uncertainty does not erase the presence of layers. The echoes we hear, the rocks we study, the shifts we observe, all point toward a world built not as one piece, but as a set of nested shells. To hold this in mind is to feel the depth beneath our step. Every walk across a field, every stone held in hand, is part of a crust that floats on something larger, something slower. Beneath that, unseen, deeper shells continue their work. They turn slowly, almost silently, yet their influence is constant. It is not a story of sharp events but of patient structures, present for billions of years and still unfolding. This thought is not a conclusion, but a gentle pause, an acknowledgement that the ground we trust is only the beginning, and that beneath it lies a hidden architecture, layered and enduring, whose full story is still beyond our reach. What if the Earth's deep interior held not only heat and motion but also subtle layers, boundaries we cannot touch yet can sense through their effects? We often imagine the core as divided simply into two parts, solid inner and liquid outer. But seismic records hint that this picture may be more complex. There are signs of stratification, meaning that within the outer core, some regions may differ slightly in composition or temperature from others. These layers are not visible, not sharp like walls, but more like gentle gradients, places where flows change pace, where materials separate slowly over time. Such stratification might act like blankets, reducing how heat escapes, or like channels, guiding how currents move. Now we pause for a moment to consider how we know this. Earthquakes send waves through the planet. When these waves reach the core, their speed and shape are altered. By studying the echoes, comparing paths across decades, researchers notice irregularities that suggest hidden layers. Some waves arrive a little earlier than expected, others a little later, as if traveling through zones of differing density. These variations are small, but repeated often enough to suggest something real. Yet here we must admit limits. Seismic data can be interpreted in more than one way. What seems like layering could also be explained by uneven flows or by chemical differences we have not yet considered. The absence of direct observation leaves us cautious. The language of traces speaks softly, and we must be careful not to mistake echoes for certainties. Now let us imagine, for a moment, what such layering might mean. If light elements like oxygen or sulfur are unevenly distributed in the outer core, they could form stratified zones. These layers might slow down convection, creating quiet regions where motion is limited. Over long timescales, this could influence how the geodynamo works, perhaps explaining periods when the magnetic field weakens. Alternatively, if heat escapes unevenly, stratification might guide the direction of flows, shaping the field in ways we do not yet fully understand. Let us wander further with a thought experiment. Suppose, in one step, the outer core were perfectly mixed, with no layers at all. Convection would be freer, perhaps more vigorous. The magnetic field might be more stable, less prone to long weakening phases. Now imagine the opposite extreme, where strong stratification divides the core into distinct zones. Convection could be restricted, the dynamo less efficient, and the field above weaker, perhaps even more irregular. Our Earth seems to sit between these extremes. The evidence suggests some layering, but not enough to silence the core's motion. Instead, the layers may act like subtle filters, guiding energy flow, not blocking it completely. This balance may explain why the magnetic field endures, yet also fluctuates, sometimes strong, sometimes weak. Now we pause and reflect on time. If stratification is real, it may change slowly as the inner core grows and the outer liquid evolves. Layers might thicken, thin, or dissolve, leaving their signatures in the record of reversals, in the drifting of poles, in the quiet weakening of the field. These are processes we cannot witness directly, but we can sense their echoes across ages. And so we close with a gentle thought. The Earth's heart may not be simple but textured, holding quiet layers within its molten sea. These hidden boundaries shape flows we cannot see, leaving traces in rocks, in waves, in skies. They remind us that even at the deepest scale, the planet carries complexity, not as a flaw but as a natural rhythm. To recognize this is not to solve it, but to accept that mystery is part of the Earth's quiet endurance. What if the very heart of the Earth, the solid inner core, is not uniform but divided, carrying within it a boundary invisible to us yet real in its effects? For a long time we pictured the inner core as a single crystal sphere, smooth and continuous. But seismic echoes suggest another possibility, that within the inner core there may be two distinct regions, an inner core and an outer inner core, each with its own properties. The differences are subtle, not like walls but more like variations in texture, the way wood grain changes direction within the same tree. This idea invites us to look deeper, to imagine a hidden structure inside a hidden structure. Now we pause to consider the scale. The inner core is already smaller than the moon, but immense by human measure. If it too has layers, then we are speaking of thousands of kilometers of iron, arranged in ways our senses cannot directly perceive. The mechanism behind such layering may lie in how crystals form under pressure. Iron atoms, squeezed into tight patterns, may align differently over time, perhaps changing their orientation as the core grew. These shifts could leave a faint signature in how seismic waves travel, faster in one direction, slower in another. By collecting many such signals, researchers begin to sense the outline of an inner boundary. Yet we must be careful. The evidence is indirect. Seismic waves are the only messengers, and they whisper faintly after traveling through the planet. Some models interpret their speed differences as proof of two regions. Others suggest the variations could come from uneven growth, or from differences in composition. Absence of direct sampling keeps all options open. The language of traces is patient but incomplete. Now let us linger on what such a division might mean. If there is indeed an inner core, it could mark a change in the history of Earth's cooling. Perhaps the earliest crystals formed with one alignment, and later, under different conditions, growth shifted to another. This would mean the inner core carries a memory of transition, a frozen record of when the geodynamo changed character. The field we live within today may bear the imprint of this ancient shift, though faint and indirect. Now we allow a gentle thought experiment. Imagine, in one step, that the entire inner core were truly uniform. Its growth would be simpler, its seismic signatures smoother. The magnetic field might behave with fewer irregularities, reversals perhaps less frequent. Now imagine the opposite. Suppose the inner core holds multiple layers, each with different orientations like concentric shells. The flows in the outer core would feel their influence unevenly, perhaps leading to complex rhythms in the field above. The shield would still exist, but with subtler variations in time and space. Reality, as always, seems to rest in between. Evidence leans toward some division, but not an extreme one. The inner core is neither perfectly uniform nor sharply layered. Instead, it may be textured by history, its atoms arranged in patterns shaped by changes across billions of years. And so we pause here with humility. The idea of an inner core is not final fact but careful suggestion, drawn from echoes faint and fleeting. Whether or not the boundary is real, the traces remind us of complexity, of depth, of history still hidden beneath our feet. To reflect on this is to sense how the Earth carries memory in form as well as in motion, writing its story not only in rocks and oceans but in the silent crystal heart at its center. What if the Earth's inner core is not simply a sphere but a place of shifting textures, with crystals growing in patterns that record time itself? Deep below, iron is pressed into solid form despite enormous heat. But it does not freeze into randomness. It arranges into crystals, like the way frost spreads across a window pane, though here on scales vast beyond imagination. These crystals may align, forming structures that influence how waves travel through them. Seismic signals hint at such alignments, as waves pass more easily in some directions than in others. It is as if the very atoms of the core are stretched, lined up by pressure, rotation, and history. Now we pause to reflect on how this happens. As the outer liquid cools, atoms at the boundary join the solid heart, layer by layer. Over billions of years, this slow crystallization may have created a fabric within the inner core, a kind of invisible grain. The Earth's rotation could have guided their orientation, pulling crystals into alignment along certain axes. If true, then the core is not just solid but patterned, shaped by deep forces that have worked in silence since the planet's youth. But here we must admit limits. We cannot hold these crystals in our hands. We know them only through echoes of earthquakes. When seismic waves cross the inner core, they reveal anisotropy, faster along certain paths, slower along others. This suggests ordered structures. Yet interpretations differ. Some models describe long needle-like crystals. Others suggest mosaics of patches, irregular but still directional. The absence of certainty keeps us cautious. Now let us linger on the language of traces. The anisotropy recorded in seismic data is not uniform. In some regions, waves move more swiftly, in others less so. This may mean that the core has zones of different crystal orientation, like layers of cloth with threads running in changing directions. Such variation could record the history of growth, marking times when cooling was faster, or when conditions shifted. These quiet differences are like a diary written in structure rather than in words. Let us wander now into a thought experiment. Imagine, in one step, that the crystals of the inner core were completely random. Waves would travel the same in all directions. The anisotropy we see would vanish. In such a world, we would learn less from seismic echoes, and the inner history of the Earth would be harder to read. Now imagine the opposite. Suppose the crystals were aligned perfectly, stretched in one grand direction. Seismic signals would be sharp, consistent, easy to trace. But the story would be simpler, perhaps less informative. Reality seems to rest between these extremes. The inner core holds order, but not absolute order. It holds randomness, but not total chaos. In this balance lies its record of change. Now we pause and think of what this means for time. As the inner core grows, the pattern of crystals may evolve. What is aligned today may shift tomorrow, though tomorrow here means millions of years. The structures we infer now may be different in the far future, as the planet continues to cool, as its heart continues to solidify. These patterns are not fixed monuments, but living records, slowly written and rewritten. And so we close with a gentle recognition. The inner core may be a sphere of crystals, aligned and misaligned, shaped by pressure, rotation, and age. It is a place where atoms arrange into patterns that carry memory. We cannot see them directly, yet we can sense their presence in the echoes of waves. To reflect on this is to remember that even at the deepest silence of the earth, form is never still. It is always growing, always arranging, leaving behind textures that whisper of history in the language of hidden order. What if the Earth's core does not turn in perfect synchrony with the surface, but instead drifts at its own pace, sometimes faster, sometimes slower? For a long time, we assumed that all of the planet rotated as one, a single body spinning steadily in space. Yet seismic studies suggest that the solid inner core may rotate slightly differently from the mantle and crust. This idea is called differential rotation. It does not mean sudden shifts, but gentle drifts, tiny differences in angle and timing that unfold over decades or centuries. Now we pause to imagine this. Picture the Earth as a sphere within a sphere, the inner ball moving in a slightly different rhythm from the shell that surrounds it. The difference is small, measured not in hours but in fractions of a degree per year. Yet, over long spans of time, these differences accumulate. The inner core may slowly turn ahead, or fall slightly behind, only to change pace again later. The mechanism lies in the balance of forces. The liquid outer core pushes on the solid inner one, dragging it through the flows of molten metal. The magnetic field, too, exerts influence, linking the motions of core and mantle. Gravity tugs in return, trying to keep the inner and outer spheres aligned. The result is not a perfect lockstep but a subtle dance, with the inner core moving to a rhythm of its own. Now we pause to admit what we do not know. Different studies have suggested different speeds, some saying the inner core rotates a little faster, others suggesting it lags behind. Some evidence even hints that the direction of drift may change over time. The absence of clear agreement reminds us of the limits of seismic signals, of how faint and complex they are after crossing thousands of kilometers of rock and metal. The language of traces here is delicate. By comparing waves from earthquakes recorded decades apart, scientists notice small shifts in travel times. These may indicate that the inner core has rotated relative to the surface. Rocks too hold clues. Patterns of magnetism in ancient minerals suggest long-term drifts in the dynamo, perhaps tied to changes in the inner core's rotation. These are not loud signals, but quiet hints accumulated patiently. Let us now step into a thought experiment. Imagine, in one step, that the inner core were locked completely, turning always in perfect synchrony with the mantle. The Earth's rotation would feel simpler, but perhaps the magnetic field would lose some of its subtle variations, its slow wanderings. Now imagine the opposite, that the inner core rotated much faster than the outer layers. Over centuries, its orientation would drift significantly, the flows in the outer core would adjust, and the magnetic field might change more dramatically, with reversals perhaps more frequent. In both imagined extremes, the rhythm of the planet would shift. Our reality lies in between. The inner core rotates differently, but not wildly. It drifts gently, its motion guided by the balance of heat, flow, and force. The surface remains steady to us, while deep within, another clock keeps time in silence. And so we pause here, with the thought that the Earth is not a single rigid wheel but a layered system, its heart moving in its own quiet way. To sense this is to recognize that even the deepest parts of the planet are not fixed but dynamic, shaping the world not with sudden jolts but with slow, patient motion, leaving their marks in the faintest of signals. What if the Earth's core were not a silent place of only iron and heat, but a storehouse of lighter elements, hidden in small but important amounts? When the planet formed, metals sank inward, creating the dense inner regions. But traces of elements such as sulfur, oxygen, silicon, or hydrogen may have remained mixed into the molten iron. These light ingredients, though minor in quantity compared to iron, could change the properties of the core in subtle but lasting ways. They might lower the melting point, affect the density, or shape how convection unfolds. Their presence would mean that the core is not just an iron sphere, but a more complex mixture, a recipe that influences how the Earth evolves. Now we pause and reflect on how we approach this idea. We cannot collect samples directly from the core. Instead, we look to meteorites believed to resemble the building blocks of Earth. Some of them contain traces of light elements within metallic iron, suggesting that Earth too might have trapped such ingredients during its early growth. We also turn to laboratory experiments. By recreating high pressures and temperatures, scientists study how iron behaves with oxygen, sulfur, or silicon. These tests reveal possibilities but not certainties. Each element alters the mixture differently, and the conditions in the deep Earth are beyond what any lab can fully replicate. The language of traces comes through indirect paths. Seismic data reveal that the outer core is less dense than pure iron would be, implying lighter elements are present. Calculations of the magnetic field's behavior also suggest that convection depends on such differences in composition. Even the rate at which the inner core grows may be shaped by how much of these lighter atoms circulate in the liquid around it. Each piece of evidence points gently toward complexity. Now let us wander into a thought experiment. Imagine, in one step, that the core contained no light elements at all. It would be denser, hotter, and perhaps more stable, but convection might be weaker. The dynamo that powers the magnetic field could fade sooner, leaving the Earth without its protective shield. Now imagine the opposite. Suppose the core held far more light elements than we think. It would be less dense, the liquid more buoyant. Convection might be stronger, the magnetic field more vigorous but also perhaps more unstable, with reversals more frequent. Our reality seems to lie between these extremes, a balance of heavy and light, of iron and subtle traces. The precise mixture is still uncertain, but its importance is clear. It shapes the motions of molten iron, the growth of the solid core, the strength of the field that stretches into space. To think of the core as pure iron is to imagine simplicity, but to accept the presence of hidden elements is to recognize nuance. These traces remind us that even in the deepest and most inaccessible parts of the planet, the story is not one of a single substance but of mixtures, of interactions, of quiet complexities. And so we pause here, with the thought that the Earth's heart is not uniform but layered with subtle influences. Lighter elements, unseen and unmeasured directly, leave their mark in density, in motion, in field. They are part of the invisible recipe that keeps the planet alive with energy. Their presence reminds us that mystery often hides in the smallest proportions, and that what seems minor can shape the rhythm of the world for billions of years. What if the Earth's core holds more than the familiar elements of iron and nickel, if hidden within it are traces of hydrogen, carbon, or even gold, sequestered in amounts too deep for us to measure? When the planet formed, heavy elements sank toward the center, while lighter materials floated upward. But the process was not perfectly clean. Some elements that we now associate with life or with the crust may also exist in the core, dissolved under immense pressure and temperature. This possibility opens the thought that the heart of the Earth is not only a furnace of heat and magnetism, but also a vault of hidden chemistry. Now let us pause and consider what this would mean. Hydrogen, for instance, the simplest of elements, may be stored in the molten metal as dissolved atoms, altering density and influencing convection. Carbon, which we know as the basis of life, may also exist there, not as coal or diamond, but as part of iron alloys stable only under such extreme conditions. Even noble metals, like gold or platinum, could have sunk in vast amounts, drawn by their affinity for iron. If so, much of the richness of Earth's crust may be but a fraction, while the deeper reservoir remains locked far below, unreachable. And yet, we must be careful. We cannot drill to the core. We can only infer. Meteorites provide some guidance, for they are thought to be fragments of the early solar system, some resembling the ingredients from which Earth was built. In them we find traces of hydrogen bound to metal, of carbon mixed into alloys, of rare elements hidden in small quantities. Laboratory experiments too, pressing iron with light elements at high pressures, show that such mixtures are possible. Still, the match is not perfect. Earth's exact path of formation may have differed, leaving its composition uncertain. The language of traces comes again from seismic wave. The outer core is lighter than pure iron, suggesting missing mass replaced by lighter atoms. How much of that deficit is explained by hydrogen, by carbon, by sulfur, by oxygen, we cannot yet agree. Each interpretation shifts the story, and we move carefully between them. Now let us allow a thought experiment. Imagine, in one step, that the core contains large amounts of hydrogen. Its density would be lower, convection easier, the magnetic field perhaps more vigorous. But the hydrogen would remain locked, inaccessible to the surface, a hidden ocean within metal. Now imagine instead that the core holds abundant carbon. Over time, some might rise into the mantle, influencing volcanic gases, altering the balance of the atmosphere, perhaps even feeding the conditions for life. Now take another step and picture the core as rich in gold and platinum, more than the entire crust and mantle combined. These metals would remain beyond reach, hidden forever, reminding us that the wealth we see at the surface is only a shadow of what lies deeper. In reality, the truth is likely mixed. The core holds some of these elements, but not in overwhelming amount. Enough to alter its density, enough to guide its convection, perhaps enough to leave faint signatures in the mantle above. But not enough for us to be certain. And so we pause here with quiet recognition. The heart of the Earth may be not just iron, but a subtle alloy, touched by light elements and heavy ones alike. It is a reminder that the planet's chemistry is layered, that the familiar and the hidden are bound together. The core remains a place of mystery, holding possibilities that shape the Earth in ways we can sense only indirectly. Its treasures, whether of hydrogen, carbon, or gold, are not for us to touch, but for us to imagine, as quiet influences on the rhythm of the world. What if the growth of the Earth's inner core is not smooth and even, but marked by asymmetry, with one side expanding faster than the other? Seismic records suggest that the inner core may not be centered exactly as we imagine, but slightly lopsided, its crystals forming more rapidly in some regions than in others. This does not mean the planet is unbalanced, but that deep within, processes unfold with quiet irregularity. The idea of asymmetry opens a window into how the Earth cools, how heat escapes, and how the magnetic field responds. Now we pause and set the scale. The inner core is believed to grow as iron freezes out of the liquid outer core. This freezing releases heat and light elements, both of which help drive convection and sustain the geodynamo. If growth is faster in one hemisphere, then over millions of years the solid heart of the Earth may become subtly uneven, with differences in crystal size and orientation. Such differences, though hidden, could affect how seismic waves travel, leaving traces for us to read. The mechanism may lie in how heat flows across the core mantle boundary. If the mantle above one hemisphere draws heat more efficiently, then the liquid below would cool faster, allowing crystallization to occur more quickly. Over deep time, this imbalance could accumulate, shaping the inner core not as a perfect sphere of uniform texture but as a body with history written into its structure. But here we must acknowledge uncertainty. Not all studies agree on the degree of asymmetry. Some seismic data suggest clear differences between east and west, while others see more subtle variation. The signals are faint, their interpretation complex. Absence of direct observation leaves us cautious, holding possibilities rather than firm conclusions. The language of traces is again our guide. Seismic waves pass more quickly through certain longitudes than through others, hinting at variations in crystal alignment. Magnetic field behavior, too, may hold clues. Some models suggest that asymmetry in inner core growth could help explain why the field is slightly stronger in certain regions. These are quiet signatures, indirect, but consistent enough to invite reflection. Let us imagine a thought experiment. Suppose, in one step, that the inner core grew in perfect symmetry, equal in all directions. The Earth's center would be simple, its structure smooth, its influence on the field more uniform. Now imagine the opposite extreme, that one hemisphere grew far faster than the other. Over eons, the solid core would drift slightly off-center, its uneven mass subtly shifting the flows of the outer core. The magnetic field above might respond with irregularities, its poles wandering more unpredictably. Our reality seems to lie in between. The asymmetry is not extreme, but present, a quiet reminder that nature prefers variation over perfection. This uneven growth may even help sustain the dynamo, creating conditions that keep the field alive. Now we pause and return to time. If asymmetry has persisted for hundreds of millions of years, then the core carries within it a record of mantle behavior, a dialogue between deep and shallower layers. To read the inner core is also to glimpse the mantle above, and the planet as a whole. And so we leave this thought gently. The Earth's heart is not a flawless sphere but a growing body, shaped unevenly by flows of heat and matter. Its quiet asymmetry is not weakness but memory, preserved in crystal patterns, reflected in waves, echoed in the field. To recognize this is to see that even the deepest symmetry is touched by imperfection, and that imperfection itself can be the rhythm that sustains the world. What if the Earth's core does not sit in stillness but trembles with its own faint oscillations, slow vibrations that ripple through the deep interior? These are not earthquakes, sudden and sharp, but long-period motions that unfold over years or centuries. We might think of them as the planet's heartbeat, too slow for us to hear, but measurable in the way seismic waves repeat with slight variations. The core, solid and liquid together, may resonate as a system, its boundaries shifting subtly back and forth. Now let us pause and set the scale. The Earth as a whole can vibrate after great earthquakes, ringing like a bell for days. But within the core, oscillations may be more persistent, driven not by sudden shocks but by the steady interactions of gravity, rotation, and magnetic forces. Some models suggest that the inner core may wobble slightly within the outer core, a slow sway guided by flows of molten metal. These movements are small, perhaps only kilometers across, but immense compared to atomic scales. They unfold so gently that only decades of patient observation can reveal them. We must admit uncertainty here. The signals are subtle, and seismic records imperfect. Different studies interpret them differently. Some see evidence of oscillations repeating over several decades, others question whether the variations come instead from uneven growth or changes in the magnetic field. Absence of direct observation keeps the question open, reminding us of the caution required when listening to faint echoes. The language of traces is delicate. Waves from earthquakes, recorded at distant stations, sometimes arrive earlier or later than expected. When compared across decades, these differences suggest that the inner core may have shifted its orientation. Magnetic records, too, may hold hints as the field responds to deep motion. Even variations in the length of day, tiny changes in Earth's rotation speed, could be tied to these inner oscillations. Each of these signs is indirect, but together they sketch the outline of movement. Now we linger in a thought experiment. Imagine, in one step, that the core were perfectly still, without oscillation. The magnetic field might be steadier, but we would lose the subtle rhythms that now provide clues to its hidden dynamic. Now imagine the opposite extreme, that oscillations were stronger, with the inner core swaying more widely. Over centuries, the magnetic field could fluctuate more intensely, the poles wandering with greater amplitude, the balance between inner and outer layers more restless. Reality seems to rest between these possibilities. The oscillations, if they exist, are gentle, influencing but not disrupting, guiding but not dominating. They are reminders that the planet's interior is dynamic not only in grand convection but also in quiet, rhythmic motion. Now we pause and reflect on time. These oscillations, if confirmed, would represent another clock of the Earth, ticking not in seconds or years, but in cycles of decades or longer. They would join the slow drift of continents, the rise and fall of oceans, the wandering of magnetic poles, as part of the planet's layered rhythms. Each is too slow for us to feel directly, yet together they shape the background of our world. And so we close softly on this thought. The core may carry its own pulse, a motion we cannot sense but can glimpse in echoes, in fields, in the smallest shifts of time. To reflect on this is to recognize that even at its deepest heart, the Earth is not static but gently moving, always alive with hidden rhythms that whisper across the ages. What if the Earth's core holds within it the memory of beginnings, a fossil record not of bones or shells but of processes that shaped the early planet? Unlike surface rocks, which erode, shift, and recycle, the core has remained isolated, sealed beneath thousands of kilometers of rock and mantle. If its structure and composition still carry the imprint of the planet's youth, then by studying its echoes we are glimpsing not only the present but also the distant past. The inner core may preserve the conditions under which it first crystallized, while the outer liquid may retain the chemical leftovers of early differentiation. Together, they might be a silent archive, one that records in density, in flow, and in composition the long evolution of the Earth. Now we pause and remind ourselves of scale. The Earth formed more than 4.5 billion years ago, from the gathering of dust and rock around the young sun. In those first millions of years, metals sank to the center while lighter silicates rose to form the mantle and crust. This process, known as differentiation, created the layered Earth we know today. But it also locked certain signals deep inside, signals that have never resurfaced. If we think of the crust as a diary, torn and rewritten over time, then the core is more like a sealed chest, holding pages still unread. Yet we must be cautious. We cannot see these records directly. Instead, we infer them through indirect methods. Seismic waves, magnetic field histories, comparisons with meteorite. Each is an incomplete translation of a hidden language. The absence of certainty does not mean absence of meaning. It only means that what we hold are fragments, enough to suggest but not to prove. Now we linger on the language of traces. Seismic anisotropy, the way waves move faster in certain directions, may be a record of how crystals first grew under the influence of rotation. Variations in density between the outer and inner core may reflect the balance of elements trapped during early cooling. Even the rate at which the inner core grows today could be a continuation of processes set in motion billions of years ago. These traces are like shadows, long and faint, stretching from the past into the present. Let us allow a gentle thought experiment. Imagine, in one step, that we could strip away the mantle and look directly into the core. Its layered textures would tell us when crystallization began, how heat escaped, what elements were present in those earliest times. Now imagine instead that the core were erased of memory, perfectly mixed and uniform. We would lose this record, and our picture of Earth's early evolution would be far poorer. In reality, the truth seems balanced. The core holds memory, but it is written in a code we cannot fully decipher, one that requires patience and humility to interpret. Now we pause and return to time. The core may preserve not only the beginning of Earth but also shifts along the way. The rise of the inner core, changes in heat flow, transitions in the magnetic field. Each event leaves some trace, faint but lasting. By comparing what we know with what we suspect, we begin to piece together a history that spans billions of years, a story told not by fossils but by atoms and flows. And so we close softly with this thought. The Earth's heart may be more than a machine of heat and magnetism. It may also be an archive, a quiet witness to the earliest chapters of the planet. Though we cannot touch it, we can sense its record in the echoes that reach us, in the field that shields us, in the rhythms that endure. To reflect on this is to remember that memory is not only in surface layers, but also in the hidden depths, where silence itself becomes a form of history. What if the Earth's core does not only influence what lies beneath but also sends quiet ripples that shape what happens far above, in the atmosphere and even beyond, in space? The magnetic field, born of motion in the liquid outer core, stretches outward like an invisible shield. It bends the charged particles of the solar wind, protects the atmosphere from erosion, and guides auroras at the poles. Without this shield, Earth's surface would be more exposed, its skies less stable, its long history of life perhaps very different. Now let us pause to set the scale. The outer core convects as molten metal moves, releasing heat and light elements. These movements generate electric currents, and currents produce magnetic fields. Together, they form the dynamo, the process that keeps the Earth's field alive. But this field is not fixed. It drifts, it weakens, it flips over time. Each of these variations at the surface is tied, however faintly, to processes deep within, where the liquid core stirs slowly, unseen. The language of traces comes from many directions. Ancient rocks, cooled from lava, lock in the direction of the field at the moment they solidified, forming a geological archive. Sediments on the seafloor, rich in magnetic minerals, also record reversals and wanderings. Even human measurements over just a few centuries show that the north magnetic pole moves, and that field strength changes. These signals are indirect, but they tie the life of the surface to the hidden motion of the deep. Now we pause to acknowledge uncertainty. We cannot say exactly why reversals happen, or why the field sometimes weakens for centuries before recovering. The patterns in the past are irregular. Some intervals saw frequent flips, others remained stable for tens of millions of years. The absence of regularity reminds us of the complexity of flows, of how sensitive the dynamo is to small changes within the liquid core. Now let us allow a thought experiment. Imagine, in one step, that the core stopped moving, the dynamo faded, and the field disappeared. Over thousands of years, the atmosphere would be eroded by the solar wind, as happened on Mars. Radiation at the surface would increase, compasses would lose meaning, auroras would vanish. Now imagine another extreme, that the field grew far stronger than today, doubling or tripling. Charged particles from the sun would be bent more forcefully, auroras might shift toward the poles, satellites would encounter different conditions. The Earth would remain habitable, but the balance of its interactions with space would shift. Our reality lies between these extremes. The field varies, but does not vanish. It weakens, it wanders, it sometimes reverses, yet it continues, renewed by the slow stirring of molten iron. In this gentle variability lies resilience. Now we pause to reflect on time. The field we measure today is only a moment in a long history, and the motions in the core that create it are slower still. What we see as change over centuries may be but the surface of cycles lasting tens of thousands of years. The linkage between core and sky reminds us that Earth is one system, joined from center to atmosphere. And so we close quietly on this thought. The invisible shield that surrounds us, guiding compasses and painting auroras, is a gift of the deep Earth. It connects what is hidden with what is seen, what is silent with what is felt. To recognize this is to remember that the core, though untouchable, is part of our daily life, shaping not only the depths but the very space around our planet. What if the warmth deep inside the Earth is not something temporary, but a presence that has been with the planet since its very beginning, a quiet reservoir that never fully fades? When we think of time in human terms, centuries already feel immense, but the Earth's hidden fire has been glowing for billions of years. This is not a blaze we can see, not flames in the way we know fire, but a steady reservoir of heat, always pressing upward from the depth. Now we gently place ourselves into this scale. At the surface, we feel only small hints of what is happening below. Warm springs emerge in certain valleys, geysers release sudden bursts of steam, volcanoes mark the spots where molten rock reaches upward. These are the surface signals of something larger. Beneath, the mantle carries slow-moving waves of energy, and deeper still, the core itself holds a furnace that has never gone out. To explain how such heat can last, we can think of two main sources. The first is leftover warmth from the planet's birth. When dust and rock clump together under gravity, their collisions released enormous energy. Imagine rolling snow into a ball, each handful making the snowball heavier. With Earth, those collisions created so much heat that much of the young planet melted into a glowing sphere. Over time, it cooled, but not completely. The crust hardened, the oceans formed, life began, yet deep inside the memory of that fire remained, trapped under layers too thick for it to escape quickly. The second source is quieter but just as important. Some elements inside the Earth are radioactive. That means their atoms are not fully stable. Over long periods they slowly change, and with each change they release small amounts of energy. Uranium, thorium, potassium. These are some of the elements that still provide heat inside the Earth. It is not dramatic. It is more like a candle that burns very slowly, not flickering, not bright, but steady across millions of years. Together, these two sources keep the Earth warm. But our knowledge here is partial. We cannot measure the exact amount of radioactive heat inside the core. We cannot sample directly from the mantle. We can only estimate, using models, using the chemistry of rocks that reach the surface, using comparisons with meteorites that may resemble the building blocks of the Earth. Each method gives us a clue, though none alone is final. What we know is guided by traces. For example, the age of certain rocks tells us how much radioactive material has already decayed, and from this we infer how much remains. The distribution of heat beneath the oceans suggests how the mantle is moving, which in turn depends on the warmth rising from below. Seismic waves change speed as they pass through hotter or cooler regions, offering yet another indirect measure. These signs are like fragments of handwriting, from which we try to imagine the whole story. Now let us allow a thought experiment to unfold. Imagine for a moment that the heat from radioactive decay were absent. Without it, the Earth would have cooled much more quickly. The mantle might have solidified, becoming rigid, continents would no longer drift, volcanoes would be silent. Without the constant motion of liquid metal in the outer core, the magnetic field might fade. And with that shield gone, solar winds could strip away much of the atmosphere. Over time, the surface might come to resemble Mars, dry, thin, exposed. Then let us take a different step. Imagine the opposite, that radioactive heat was much greater than it is. In this scenario, the mantle would flow more quickly, volcanic activity would be constant, the crust thinner and less stable. Life on the surface would face frequent upheavals, perhaps never finding the long stretches of calm needed to thrive. What we live within is a balance. The heat is enough to keep the planet active, but not so much that it overwhelms stability. This balance may not be permanent. Slowly, the Earth continues to cool. In the far future, the core may solidify more fully, the magnetic field may weaken, tectonic motion may slow. These are changes we will not see in our short time. Yet they remind us that the Earth, too, has a lifespan measured in rhythms we can only glimpse. For now, the signs we observe, the volcanic arcs, the spreading seafloor, the restless shifting of continents, are proof that the inner warmth remains strong. We cannot touch it, we cannot measure it directly, but we see its language written in stones and landscape. It is a language of patience, not of haste. To hold this in mind is to sense a deeper scale of time, one that flows beneath our own days and centuries. The Earth's heat is part of that slow current, a background presence, neither fully understood nor fully hidden, reminding us that even in silence and depth, energy endures. This is not a final answer but a pause, a recognition of warmth that began with the planet itself and still lingers, shaping the world in ways both subtle and profound. What if the secrets of the Earth's core will never be fully revealed, yet their quiet influence will always be with us? For all our measurements, for all our models, there remains a veil that cannot be lifted by drills or by direct touch. The core is too deep, too hot, too remote. But this very distance makes it enduring. It reminds us that knowledge is often shaped by absence as much as by presence, by echoes and shadows rather than direct sight. Now let us pause and consider the scale of our journey. From the crust beneath our feet down to the inner heart of iron, we have traveled in thought through thousands of kilometers and billions of years. We have followed seismic waves, read magnetic fields, compared meteorites, and traced isotope. Each clue has been partial, each explanation tentative. Yet taken together, they have given us a picture of a world alive from its very center outward. A world that moves, that shields, that remembers. Still, much remains unknown. We cannot be certain how the core began crystallizing, or how it will evolve in the far future. We cannot confirm whether hidden elements wait within it, or how deeply its rhythms affect the surface. Absence of proof is not proof of absence, and so we walk carefully between possibilities, holding space for what may yet be found. The language of traces is what stays with us. Seismic echoes, variations in the length of day, shifting poles, ancient rocks preserving old fields. Each is a page in a dispersed archive, a record not written in ink but in waves, in atoms, in time. Reading them is slow work, requiring patience, humility, and imagination. Now let us linger in a thought experiment. Suppose, in one step, that the veil could be lifted and the core laid bare. We would see its textures, its flows, its secrets, and the mystery would vanish. Yet perhaps the mystery itself is what sustains wonder. Now imagine instead that the veil thickens, that signals fade, that we lose the ability to read its traces. We would still live under its influence, guided by its magnetism, shaped by its heat, but the connection would feel more distant. In reality, we live in balance, close enough to sense, distant enough to question. The mystery remains, and in remaining, it teaches us to listen quietly. Now we pause and return to time. The core will outlast us. Its growth will continue for billions of years, long after mountains have eroded, long after oceans have shifted. The field it sustains may wax and wane, may reverse, may even fade in a distant future, but its influence will stretch across ages far beyond human memory. To reflect on this is to place ourselves in perspective, to see our lives as brief moments within the larger rhythm of the planet. And so we close gently. The Earth's core may hold secrets we do not yet understand, and perhaps never will. But those secrets are not locked away in silence. They speak through waves, through fields, through the slow turning of time. If we listen with patience, we hear them, not in certainty but in possibility. And if the rhythm of such reflection feels close to us, we already know how to carry it forward, quietly, steadily, allowing the mystery to rest, while we rest with it. What if the hidden heart of our planet is not one simple mass, but a structure with two distinct faces, each playing its role in silence? Scientists describe the core as having an inner solid part and an outer liquid one. This picture is not born from direct sight, for no tool can reach so far, but from patterns, echoes, and calculations. The idea is that at the very center lies a dense seed, a sphere made mostly of iron, locked in place by immense pressure, solid despite unimaginable heat. Surrounding it is a layer of molten metal, still fluid, still moving, like a vast ocean of glowing iron that never fully cools. Together, these two parts create a quiet partnership, one still and rigid, the other restless and flowing. To understand why the inner part is solid, we may think of water turning into ice. On the surface, water freezes when it becomes cold enough. In the deep earth, it is not cold, but the crushing weight of all the layers above presses so strongly that even heat cannot keep the metal liquid. Pressure locks atoms into place, forcing solidity where we would expect melting. Around it, in the outer layer, pressure is a little less severe, and the same iron remains liquid, flowing slowly, currents shaping movements we can only imagine. We do not see these motions directly. We infer them through signs. The way the magnetic field behaves, the way seismic waves pass through. Some waves can cross solid iron but not liquid. Others bend and shift at boundaries. From this hidden language we build our models. Now we pause and admit the uncertainty. The boundary between inner and outer core may not be as simple as a sharp line. Some suggest there could be zones of mixed behavior, places where matter is neither fully solid nor fully liquid. Others imagine that the inner core may itself contain layers, perhaps with crystals aligned in patterns. These are possibilities, glimpsed through limited evidence, still awaiting clarity. The traces we study come mostly from earthquakes. When the earth trembles, waves travel in all directions. Some pass through the inner regions and return altered. Their paths are our clues. By comparing their arrival times, by noting how they weaken or strengthen, we draw outlines of hidden structures. It is a delicate process, like listening to distant thunder and guessing the shape of the storm. The field of magnetism is another marker. The liquid outer core, in motion, seems to act like a dynamo, generating a magnetic shield that extends into space. Without this motion, the shield might fail. The solid inner part may play a stabilizing role, anchoring the process, though we cannot be certain. This interplay of solid and liquid, of seed and ocean, is part of why the Earth's heart continues to influence life at the surface. Let us imagine for a moment a change in this balance. Suppose the inner core were absent, leaving only liquid. The flow might be less organized, the magnetic shield weaker, more unstable. Over long spans, the atmosphere could suffer, leaving life more exposed. Now let us imagine the opposite, that the outer part froze completely, leaving only a giant solid sphere. The dynamo effect might vanish, the field might fade, and once again, the surface would face a harsher sky. Neither extreme is the case today. Instead, we live with a balance, solid within, liquid without, a system that has endured for hundreds of millions of years. Yet this balance is not fixed forever. The inner part is thought to be slowly growing, as the planet cools, with more of the liquid freezing onto it over time. The outer ocean, in turn, becomes slightly thinner. These are not changes we will see in our lives or even in the lifetime of civilizations, but in the quiet scale of geologic time, they matter. We may think of the Earth as carrying its own clock, each tick a tiny growth of its inner heart. We cannot say exactly how fast this clock runs, nor what its final outcome will be. What we can say is that its traces are visible in the shifting of the field, in the echoes of waves, in the restless surface above. To linger with this thought is to sense the layered nature of the Earth's depths, not as something distant and alien, but as part of the same whole that gives us ground to stand on and a shield to breathe under. The dual nature of the core is not just a scientific model, but a reminder of balance, between movement and stillness, between heat and pressure, between what we know and what remains hidden. And so we pause here, holding the image of a solid seed surrounded by a flowing sea, a picture drawn from signs rather than sight, an understanding that is partial yet quietly powerful, guiding us as we continue to listen to the Earth's heart. What if the Earth itself could whisper, sending messages from its deepest parts, not through words but through waves that ripple after an earthquake? Each tremor, each sudden release of energy, travels outward in all directions, passing through layers we cannot see. These vibrations are our windows into the unseen. They move like echoes in a great hall, some fading quickly, others traveling long distances, each shaped by the material they pass through. By listening carefully, we begin to hear the structure beneath our feet. Seismic waves, as scientists call them, are simply vibrations of the ground. When a quake occurs, two main types are born. One is compressional, like the back-and-forth motion of a spring. The other is shear, like the sideways shake of a rope. Each type behaves differently depending on what lies in its path. The compressional waves can pass through both solids and liquid. The shear waves, however, cannot move through liquids. This simple difference has been one of our most valuable clues. When we map where shear waves stop, where they bend, where they disappear, we gain hints about the hidden architecture of the Earth. Now let us pause and notice how indirect this method is. We are not peering into the core with cameras. We are reading shadows and silences. The places where waves fail to appear tell us as much as the places where they arrive. It is like noticing that a sound did not echo in a certain corner of a room, and from that absence guessing that something soft is hanging there. The Earth's core revealed itself this way. Shear waves vanish when they reach the outer core, suggesting it is liquid. Compressional waves slow down, bend, and reappear, telling us of the boundaries and densities. From countless earthquakes recorded across decades, a pattern emerged, a hidden sphere, partly solid, partly molten, deep below us. Yet even with all these signs, we remain cautious. Seismic waves are not simple to interpret. They scatter when they meet complex structures, they bend in ways that can be modeled differently. Sometimes one dataset suggests one picture, another suggests a slightly different one. Models are adjusted, redrawn, tested again. The deeper we go, the more uncertain the details become. Still, over time, the outlines stay consistent. A layered Earth with a liquid shell around a solid heart. Now let us think about the language of these waves as an archive. Every quake, no matter how small, becomes a probe into the planet. The recordings from seismic stations, millions of them now stored, are like pages in a book. By comparing one tremor to another, across decades, across continents, we refine the image. Slowly, as if developing a photograph in the dark, the blurry shapes of the interior sharpen. We may not see details clearly, but we recognize forms. Imagine for a moment a world without quake. It would be calmer on the surface, perhaps, but our knowledge of the deep earth would be far poorer. Without waves to carry echoes, the hidden core would be much more mysterious. We would know less about the liquid metals, less about the solid heart. In this sense, each earthquake, though disruptive for those nearby, provides the planet's own way of telling us about its structure. Now let us take another step in thought. Suppose the waves behaved differently, passing easily through both solids and liquids. Then the clues we rely on would be gone. The Earth's core might remain only a guess, with no strong evidence to support its dual nature. We might imagine many possibilities but never find the marks that point one way or another. The fact that waves behave differently is not just a physical property but a gift, a distinction that allows us to read the planet's depth. We return here to humility. Even with all these tools, our knowledge is partial. We do not know the exact composition of the core. We cannot trace every motion of the molten metal. We cannot be certain how the boundaries shift over long spans of time. But through echoes, through silences, through bending paths, we hear enough to know there is something there, vast and enduring. The study of seismic waves is less about certainty and more about patience. Each quake adds a little more detail, each measurement a new line in the drawing. Together, across generations, they form a quiet dialogue between the earth and those who listen. And so we pause with this image in mind, a planet that trembles not only in fearsome bursts, but also in whispers that cross oceans and circle the globe. In these vibrations lies a hidden archive, one that tells us about solids and liquids, about boundaries and depths, about the heart of the earth itself. It is not a complete language, but it is enough to guide us gently, enough to remind us that even silence and absence can carry meaning if we take time to listen. What if the slow movements of molten metal deep below us give rise to an invisible shield, a magnetic veil that surrounds the earth? This shield is not something we see with our eyes as we look at the sky, yet it is always there, shaping the way our planet meets the energy of the sun. To imagine it, we need to place ourselves not only beneath the surface but also far above it, into the thin boundary where Earth's atmosphere meets space. There, charged particles from the sun stream constantly, a wind that never truly stops. When this solar wind meets the Earth, it does not strike directly. It is guided, bent, and softened by the magnetic field that springs from the restless outer core. The mechanism may sound complex, but in simple terms it is similar to how an electric dynamo works. A dynamo is a device where moving metal or wires create a magnetic field. Deep within the Earth, liquid iron and nickel swirl slowly as the planet rotates, setting up currents of motion. These currents, though invisible to us, generate electricity, and that electricity in turn produces magnetism. The result is a field that extends far into space, forming a protective bubble around our world. We often call it the magnetosphere. Now we pause to acknowledge how little of this process we can witness directly. We cannot watch the metal flow. We cannot place instruments into the core itself. Instead, we rely on indirect markers. One of the clearest is the way compasses behave. For centuries, they have pointed north, not because of the stars or geography, but because of this hidden field. Another marker is more subtle. In the rocks of the crust, tiny magnetic minerals align with the Earth's field at the moment they cool. These minerals keep their alignment for millions of years, preserving a record of where the magnetic poles once lay. By studying these rocks, spread across continents, we discover that the field has wandered, shifted, even reversed many times. Such reversals are not something we have seen directly in our own lives, but the rocks remember them, quietly keeping an archive of the invisible. Now we may imagine what would happen if the magnetic shield did not exist. Step by step, we can picture the consequences. Without it, the solar wind would strip away the outer layers of our atmosphere, just as it likely did on Mars. Over long timescales, air would thin, water could be lost, and the surface might become harsher, less friendly to life. Another thought experiment takes us in the opposite direction. Suppose the field grew far stronger, fluctuating wildly. Compasses would become unreliable. Navigation would suffer. The auroras, those dancing lights near the poles, might appear more often, even in places far from the Arctic or Antarctic. Yet too much turbulence could disturb satellites, power grids, and delicate instruments. Once again, balance matters. At this moment, the field is not steady. It drifts, it weakens and strengthens, though in cycles so long that human lifetimes notice only small changes. Its poles wander slowly, sometimes reversing over spans of hundreds of thousands of years. We do not know exactly when another reversal will occur. We cannot predict its pace with certainty. What we do know comes from patterns written in stone, from measurements taken by satellites, from centuries of quiet observation. These traces remind us that the shield is dynamic, not fixed. Now let us linger for a moment on the visible beauty the field creates. When solar particles are guided into the atmosphere near the poles, they cause gases to glow. The result is the aurora, gentle curtains of green and red and violet, shimmering in silence. This is the rare moment when the magnetic field becomes visible, not just a force but a spectacle, a reminder of the unseen engine at work. But most of the time, the shield is quiet. It is protection without display, a background presence we take for granted. Its value lies in its invisibility. We live beneath it, breathe beneath it, rarely aware that it is there. And here we must pause once more to recognize uncertainty. The exact flows in the core remain hidden. The models we use to explain the field are incomplete. We know some parts of the story, not all. Absence of knowledge does not mean the absence of process. It simply means that the heart of the earth continues to keep many of its secret. To close this reflection, let us hold the image of a shield we cannot see, born from movements we cannot touch, yet shaping the life we know. It is fragile and enduring at once, a veil stretched across the space between earth and Sunday. Not a permanent certainty, not an eternal stillness, but a balance unfolding quietly across the longest scales of time. What if the memory of the Earth's invisible shield could be read not in the sky, but in the stones beneath our feet? Long before people built instruments, the planet itself was keeping records of its magnetic field, storing them quietly in minerals as they cooled from molten states. When lava hardens, or when sediments settle and compact, tiny grains of iron-bearing minerals align with the direction of the Earth's magnetic field at that moment. They become like frozen compasses, holding the orientation of poles from a time long past. These grains are unimaginably small, yet together they form archives that last for millions of years. By studying them, we discover that the magnetic field has wandered, weakened, and even reversed many times in Earth's history. Let us pause here for a moment. The field we take for granted today, steady enough to guide compasses and protect our sky, is not always fixed. Rocks tell us that the North and South poles have swapped places more than once. These reversals are not sudden in human terms, but they unfold over thousands of years, a slow turning of the planet's magnetic memory. We cannot witness one from beginning to end in our own lives, but we can trace their echoes through these mineral archives. The process of reading these records is delicate. Scientists measure the magnetization of rocks with instruments sensitive enough to detect signals weaker than those of a handheld magnet. They gather samples from ancient lava flows, from layers of the seafloor, from sediments deep in lakes. Each sample holds a faint signal, but when combined with many others, patterns emerge. The seafloor, for example, shows stripes of alternating magnetic orientation, created as new crust forms at mid-ocean ridges while the field above it shifts over time. These stripes stretch for thousands of kilometers, silent testimonies to a restless shield. Now we gently turn to the limits of what we know. While the records confirm reversals, the reasons for them remain less certain. Perhaps changes in the flow of liquid iron deep in the outer core trigger instability. Perhaps the growth of the solid inner core influences the balance. Or perhaps processes we have not yet imagined are at play. The stones preserve the fact of change, but not the cause. Our models simulate possibilities, but no explanation yet holds all the answers. The absence of certainty does not mean absence of process. It simply means the Earth still holds secrets we have not unlocked. Now let us wander into a thought experiment. Suppose, in one step, that the field ceased to reverse altogether, fixing itself permanently. Over long spans of time, certain traces in rocks would no longer appear. The archives would lose a layer of information, and our planet would be quieter in its magnetic story. Life on the surface might continue, shielded as before, but the geological memory would be simpler, less varied. Then imagine the opposite step, that reversals occurred much more often, perhaps every few centuries. Navigation, reliant on stable poles, would be less reliable. Migrating animals, many of whom seem to sense the field, might face confusion. Technology in our age, sensitive to geomagnetic shifts, could require constant adjustment. The planet would still be protected, but the surface experience of that protection would be less stable, more dynamic. In reality, what we see is something in between. Reversals happen irregularly, sometimes separated by millions of years, sometimes by hundreds of thousands. The field weakens and strengthens, but not in a predictable rhythm. Rocks remember these shifts as faithfully as tree rings remember seasons, but unlike tree rings, the intervals are not steady. They are reminders of a system complex beyond our complete grasp. Now we pause again and note the beauty of this hidden archive. The Earth's memory is not kept in books or carvings, but in orientations of tiny crystals, in patterns across the ocean floor, in sediments untouched for ages. These quiet witnesses speak of a shield that breathes over. Geological time, not fixed, not fragile, but dynamic. To reflect on this is to sense time on a scale beyond our own. Human civilizations rise and fall within spans too short to notice a full reversal. Yet the rocks, waiting in silence, record them all. Their patience is their strength, their alignment a quiet language. So we close gently with the thought that the Earth remembers its own shield, not in dramatic ways, but in quiet, magnetic lines written into stone. These traces do not give us every answer, but they remind us of continuity, of change, of balance. And they leave us with the humility that much of what lies beneath our feet is still speaking in a language we are only just beginning to understand. What if the story of the Earth's core is not only about what happens inside, but also about how time itself has been shaping and reshaping it far beyond any human scale? When we think of billions of years, it can feel almost impossible to grasp. Our lives span only brief moments compared to the quiet patience of the planet. Yet within this stretch of time, the core has not stood still. It has cooled, shifted, and slowly changed its balance, leaving traces we can read in the layers above. To imagine this more clearly, let us think of the Earth as a slowly beating heart. Its rhythm is not in seconds or minutes, but in ages. Each pulse may take millions of years, yet those pulses have left their marks. The crust above is cracked and folded, mountain ranges rise and fall, oceans open and close. These movements, though they seem to belong only to the surface, are tied to the deeper warmth and slow energy that rise from the mantle and core. If that hidden heat had been lost quickly, the surface would now be quiet, still, without the motion of plates. Instead, over vast spans of time, the planet has remained alive. Now we pause for a moment on what we do not know. We cannot measure the temperature of the inner core directly. We cannot see its changes across time with our own eyes. What we know comes from hints, traces in rocks, records in sediments, patterns in the seafloor. Each layer is like a page in a book that the Earth has been writing for billions of years. We read that book carefully, yet much remains unclear. Some models suggest the inner core is growing slowly as the outer core cools. Others suggest that growth is uneven, perhaps stronger in some regions than others. These are not certainties, but possibilities, glimpsed through indirect evidence. Now let us reflect on the language of traces once again. Ancient lava flows contain minerals aligned with magnetic fields that no longer exist. These minerals keep the memory of times when the poles were reversed, when the field was weaker or stronger. By piecing together these patterns, we build timelines of change. Ocean floors, spreading slowly at ridges, record stripes of magnetic alignment, showing us a barcode of reversals stretching back millions of years. Even ice cores, though far younger, preserve particles from solar storms, themselves shaped by the state of the magnetic field. All of these archives point to a deep interior that is not constant but slowly shifting, leaving echoes across the whole planet. Now let us drift into a thought experiment. Imagine for a moment that the Earth had cooled much faster, and that the core had solidified long ago. In such a case, the magnetic field might already have faded. The atmosphere could have thinned, the surface exposed more directly to solar winds. Life might have struggled to survive in such a harsher environment. Now take the opposite step. Imagine the Earth retaining far more heat, so much that its surface was constantly reshaped by eruptions, with continents splitting and reforming in centuries instead of eons. The stability needed for long stretches of calm, for forests to grow and civilizations to rise, might never have come. Neither picture is our reality. The Earth has found a balance, a slow rhythm that has allowed both change and continuity. Its deep processes move on scales too large for us to see, yet their marks are all around us. Mountains, oceans, shifting fields, all are chapters of a book written in deep time. And yet, even with these signs, we cannot say with certainty how the future will unfold. The inner core may continue to grow, the outer core may continue to cool, the magnetic field may wander and reverse again. These are not abrupt events but gradual transformations, unfolding across spans beyond our imagination. To hold this thought is to feel the depth of time itself, the scale at which the planet lives and breathes. It is not a scale that belongs to us, but we are part of it nonetheless. Our lives take place on the surface of a world whose heart still moves, still changes, still carries the memory of beginnings. And so we pause here, with the quiet recognition that the story of the Earth's core is also the story of time, time measured not by clocks or calendars, but by the slow patience of stone, metal, and memory, written in silence beneath our feet. What if the solid heart of the Earth moves at a slightly different pace than the rest of the planet, turning with its own rhythm, like a clock that ticks just out of sync with the one we hold in our hand? The idea is gentle, almost imperceptible, and yet it carries weight. We are used to thinking of the Earth as one body, spinning together. But deep below, the inner core, locked in its immense pressure, may rotate just a little faster or slower than the mantle and crust above it. The difference is not something we could notice on the surface from day to day. It is measured only through the faintest signals, through the echoes of seismic waves that travel differently depending on how the core is aligned. Scientists call this process differential rotation. In simple terms, the layers of the Earth are not rigidly fixed together. The outer core, liquid and mobile, separates the mantle from the solid inner core. This allows the inner sphere to drift slightly in its rotation, almost as if it were floating inside a shell. We do not know the exact pace of this drift. Some studies suggest the inner core may rotate a little faster, completing an extra turn over the course of a decade. Others suggest it sometimes slows, even pauses before resuming. These are not certainties, but careful interpretations of limited data. Now we pause to admit the challenge. We cannot place markers on the inner core. We cannot watch its movement directly. Instead, we listen to seismic waves from earthquakes. When waves pass through the inner core at different times, we compare their travel. Tiny differences hint at rotation. Yet these measurements are subtle, often at the edge of what our instruments can detect. From them, we build models, but the models are open to revision. Absence of proof for one pace does not prove stillness, and signs of movement may mean more than one possible pattern. What we can say is that the inner core may not move exactly with the surface, and that this offset, however small, could matter. Now let us gently consider the language of traces once again. If the inner core does rotate differently, then the magnetic field generated by the outer liquid core may feel its influence. Patterns in field strength, in pole wandering, may carry the mark of the core's subtle drift. Rocks on the surface, with their magnetic memory, could be recording not only reversals and fluctuations but also echoes of these deeper rhythms. The archives are incomplete, but they hold suggestions of long, slow pulses from within. Let us wander into a thought experiment. Imagine, in one step, that the inner core rotates steadily faster than the surface. Over centuries, its offset could alter the balance of flows in the outer core, perhaps changing the magnetic field more strongly, perhaps creating longer or shorter intervals between reversals. Now let us take another step. Suppose instead that the inner core slows, becoming almost still. The outer liquid would continue to move, but the stabilizing influence of the inner seed might lessen. The field could waver, the shield above us changing in subtle ways. In reality, what happens may be gentler still, a rhythm of speeding up and slowing down, like a pendulum swaying with a very long period. We do not yet know the details, only the possibilities. And here we return to humility. Our knowledge of the core's motion rests on signs faint and fragmentary. Instruments improve, methods grow sharper, but certainty remains elusive. What matters is not that we know every detail now, but that the earth leaves us hints, and we are learning to read them. To hold this thought is to picture the earth as layered clocks, each keeping time in its own way. The crust and mantle rotate with the rhythm of days, marking the passage of time we live by. The inner core may keep another rhythm, slower, subtler, almost hidden. Both rhythms together shape the planet we call home. We end here with a pause, recognizing that the drifting heart of the earth may hold a story still unfolding, written not in seconds or years, but in the long cycles of deep time.